So welcome to today's class. We are going to discuss or continue our discussion on hidden Markov models. Okay, the reference is PRML section 13.2. Okay, so what is the hidden Markov model? It is basically it takes care of the temporal evolution. Let us say you have a particular state S which is changing with time, right? And each state can give rise to an observed phenomenon. Okay, so this is something like this we saw in the last class. So you have a state denoted by Z which gives rise to something called X, and this X is observed. But Z is not observed. Z is a hidden state. So we give an example of temperature versus season. Temperature is the observed thing. We can measure temperature, but season is a latent variable which, okay, if I do not know the date today, I cannot tell the season, right? So from the temperature itself, I have to infer, okay, this looks like summer season, this looks like winter season, rainy season. Just from temperature, I have to infer which season it is. Basically, season is a latent variable which I do not observe. So this is the kind of thing we saw. But then there is a temporal evolution associated, which means my Z is a function of time. So I call this as Zn. And X is also a function of time, or the temporal discrete time. So I'm observing X at consecutive intervals, and similarly the underlying Z is also changing, or I'm assuming that Z is changing, that is why the X is okay, I can't say that. I can say the distribution is changing. So Z characterizes the distribution of X. So look at this, probability of X given Z. So Z characterizes the distribution of X, right? Of course, X is changing even if the Z is same, but the underlying distribution is stationary. But if I assume, okay, that the underlying distribution also is changing, so Z is a discrete thing we discussed. Z is a discrete random variable, which means I have a discrete set of a finite set of possible underlying distributions. So this is the general latent variable, discrete latent variable model, right? And we assumed that this Z satisfies which property? First order Markov property, which means that this Z at time n depends only on Z at time n-1. It does not depend on time n-2 if n-1 Z is given, right? So conditional independence. So my Z is independent of all previous observations if Zn-1 is given. Sorry, not observations, but the latent states. Now, I can split this thing into this thing. We derived this in the last class, that how this is the transition probability. From the previous Zn-1, I go to Zn, and this is the emission probability, which is, okay, I can expand this in this way. I can say this is Zn-1, which gives rise to Zn, and also it results in Xn-1. And this is further caused by previous states. This is leading to future states. This we have discussed. Okay, now, so Zn given Zn-1 is the transition probability, and Xn given Zn is the emission probability. This is totally the joint probability of HMM. We took this example. So let's see what we can do with this model. Okay, if a trained HMM is given to you, right? An HMM is given to you. Can you generate new data from it? How will you generate new data? How will you sample new data from this model? How will you sample new data from this model? I've given you a model. Can you generate data from this model? Define. Okay, I don't have any Zn. There is no notion of next. Okay, so we first randomly sample initial state Z1. Okay, so you sample Z1 from probability of Z1, which is pi Z1, right? This thing. So you sample Z1, then what do you do? So I obtained this Z1. Now
we obtain an X corresponding to it and an X.
yes, very good. Then I can sample X corresponding to it, X1 from probability of Xn given Zn, sorry, X1 given Z1. Then, so I obtained X1. Next, I will obtain Z2. I will transition to the next state, or sorry, the next value of the same state. Means at the next time instant. So I sample Z2 from probability of Z2 given Z1. Similarly, then I will sample X2, and in this way I can proceed. Right? This is how I sample new data from the given model. Next question. If you are given a new observation Xn, can you infer Zn? Okay. If I give you an observation Xn, can you infer the underlying hidden state? Yes or no? Okay, assume this is just one time instant, only one sample. I give you one observation, can you infer the underlying state? Pardon? I don't know. Let us assume here, I am just given one sample. Can you infer the Zn from Xn? How will you do that? Maximum likelihood approach. Okay, tell me what will you use? What is the likelihood? Pardon? Very good. Probability of Xn given Zn. This is the likelihood, and you want to maximize this. So your Zn star is equal to right. This is the maximum likelihood thing. Okay. Yes, this is called maximum likelihood estimation. What else can you use? You can use map estimation, where you will do Bayes rule, right? That also you can use. Okay, so you know how to estimate the underlying state given the observation. Now you can use this for classification, right? If you know how to do this, you can use this for classification. You want to classify which season it is today. So you can just observe the temperature and you can give your inference on the underlying season. Okay, this is the season because my temperature is somewhere around 30 degrees Celsius. So there is it's very likely it's not summer, okay, rainy season. But it is very unlikely that it is winter, right? Okay, so just a clarification here. Zn refers to single observation at the nth time instant or the nth day in our case. We are not here. We are not estimating the parameters of the model. We are estimating the underlying distribution. Means we are not estimating the model parameters. We are just estimating one out of many models. Let's say there are 6 seasons. So Zn can take 6 values, 1 to 6. And I want to estimate, given this temperature, which model generated this data. So I'm not training Px given Zn, comma theta. So okay, to be more precise, there are thetas as well. If this is a Gaussian mixture model or Gaussian model or Laplacian model, Poisson model, whichever. So this will be probability of x comma Zn comma theta. Right? So these are already known. Assume that these are known. Right? This model is given a trained HMM. Right? So these are known. We are not estimating that. Good question. Okay. Now come to sequence. If you know Zn minus 1 and you are observing Xn, right? You're given the model, you're given what was the weather yesterday, what was the season yesterday. And today I am giving you the temperature and I'm asking you what season it is today. What will be your answer? Or give me yes, you can use MLE, but give me a distribution of what is the probability that today is winter or summer or which season it is. Huh? Pardon? You can combine both the predictions. How? Yes. How do we combine? Map. Okay, I want to estimate the distribution, so map won't work, MLE won't work. I want to estimate P of Zn given Xn comma Zn minus 1, right? Let us say, what is the probability that Zn, means the temperature today or the season today is K, given the temperature Xn and yesterday's season Zn minus 1, J. So what is the probability that today is K season? You can see here. So you can see I can now just use probability rules and break it down, and means here I am using Bayes' theorem because I want to estimate it in terms of the known quantities. So I am using P of Xn given Zn. This is given. This is what I know, right, from the model. P of Xn comma Zn minus 1 into P of Zn given Zn minus 1. This is simply the Bayes rule, right? I've simply applied Bayes rule because I know P of Xn given Zn. Okay, this Zn minus 1, what will happen to this? Yes, they are independent because P of Xn given Zn will be independent of Zn minus 1, so that can be dropped. So that's why you got P of Xn given Zn. And this term is the transition probability. This is the emission probability. Okay, from this season, what is the probability this temperature will be emitted? And this is the transition probability. If yesterday was this season, what is the probability that today is this season? Right? So just I've written the same thing. Now, using our notations which we have introduced in the last class, P of Zn given Zn minus 1 can be written like this. I know Zn minus 1 is J, so AJK, probability of transition from jth state to kth state, right? J could be 1 to 6, K could be 1 to 6. And AJK is the matrix which we defined in the last class. It is a general representation of transition. Now this is emission probability P of Xn given this season. So you can model it with any, we discussed in the last class, any model or neural networks or probabilistic model, whatever you want, right? Okay. Okay. Once you find this, you can choose. This will be your map estimate. Argmax K probability of Zn given Xn Zn minus 1, right? This is your map estimate. But okay, the goal was to estimate the PDF, which we have done. Okay, now a more difficult question. If you observe xn comma xn minus 1, okay, which means, okay, you observe temperatures from some first day to nth day, what is the probability of seasons? Like, what was the season on the first day, what was season on the second day, and similarly on the nth day? What is the probability of Zn given Xn? Means all these Zs given all these X. So for this again you can use Bayes rule because you know Px given Z from your model. So this is what you have written, and it basically boils down to this thing, which is essentially the joint distribution of x comma z, right? The same thing. Okay, now this question is important. How do you estimate the most likely sequence Z1 to Zn? This is not trivial, right? Now I am not asking you for one season. I am asking you the entire evolution of season, the entire trajectory of season. This is a difficult problem. How will you solve this problem now? Okay. So let us write it down in terms of joint distribution. So in terms of, okay, let us say we are doing, what is it called, the map estimate, right? This is the map estimate, probability of x comma z divided by probability of x, the maximum of, you're maximizing the joint distribution. So you are maximizing the joint distribution. What value of z will maximize, that value you assign. This is a very complicated distribution. Basically, the complexity is very large, means the search space is very large. So let us say there are 100 days of data. Each day can take 6 temperatures. So what is the search space? What is the search space? There are 100 days and each day can have 6 different seasons. So what is your search space to optimize this joint PDF? Means how many possible vectors of Z? 6 raised to the power 100. Very good. So on the first day you can take 6 values, second day you can take 6 values, third day 6 values. So multiply everything, you will get 6 to the power 100 vectors. So this problem is, I'm not going to solve it. If you are interested, I can give it as an exam problem. So this is intractable, means very difficult to solve, especially for large search spaces. This becomes impossible. But we can use the structure of the model and we can use some approximations to make it tractable. One method which you already know, which one? One method which you already studied in last to last class. Which one is that? Okay, let me show it pictorially, then you will have better understanding. Okay, so pictorially, let me represent this joint distribution now pictorially. So what is happening? You are sitting in some state k equal to 1 or something. Zoom. Is it better now? Okay. So let us say you are sitting in some particular state, right? You have to make, first you have to emit something, then you make a transition, emit something, make a transition, emit something, make a transition, emit something, right? This is the general trend. Now what you can do is, okay, you are sitting in this state with some initial probability pi of this state, then you emit something, p of x1 given z1, right, which is this term, p of x1 given z1 you emit, and then you make a transition to the next state or either to a self transition on the same state, or so like there are 3 possibilities. You either stay on the same state, go to 2 or go to 3, right? So that part will be here, transition probability, p of zn given zn minus 1. And then when you go to the next state, you will emit something there as well, right? What will that be? P of xn given zn, right? And then again you make a transition, this term, and then you again emit something. Then you again make a transition, again emit something. And all these probabilities or the log of these probabilities, they keep adding and the probabilities keep multiplying, right? So this is the kind of basic model. But now I can unroll this model in time. How? I can say, now this is my state at time n equal to n minus 2. I could be here or here or here. Let us say I am here at k equal to 1, right? What I will do, I will emit something, right? And then I will make a transition either to first state or second state or third state. To one of these at n equal to, sorry, at time equal to n minus 1, I'll be in one of these possible states. And then again I will emit something from there. Then I will go to the next state and emit something there. So in this way, I can formulate a cost function which is associated with each transition and each emission, right? Each transition will cost me something and each emission will cost me something or reward me something, right? So each transition and each emission. In this way, I can formulate a cost function associated with each node. Now I have to find the sequence of nodes which maximizes or minimizes my cost function. What approach can I use? You have seen this some classes ago, maybe 2 classes ago.
Greedy.
What is that greedy? Anybody?
We locally maximize
Dynamic?
time warping.
Dynamic time warping, yes, thank you. So dynamic programming or dynamic time warping, these things you have seen. That how do you optimize the path of basically if you're given a matrix or lattice, whatever, you want to find the best path which will optimize a particular cost function, then you know how to use very greedy approach which is DTW, dynamic time warping. This is what we are doing, or this is what we are going to discuss now. Okay, so I can use dynamic time warping. For that, I have to formulate my cost associated with each node as well as the total cost function, right? So this is my total cost function, capital D. I have kept the same notation. So this notation is not generally used for HMMs, but to be consistent with our DTW discussion, I kept the same notation. So no, doesn't matter, notation can be anything. So the total cost of the path Z1 to Zn can be broken down as sum of these things, basically summed over cost of each Zn dash. Since this is a Markov model, this cost also depends on the previous state because the transition will bring a cost, right? So this becomes this, the transition probability, log of that, plus the emission probability, the log, right? So this is your cost associated. So let us say if I am here at Z1 or okay, Zn minus 2, I have some cost capital D Z1 to n minus 2 and then I make a transition to n minus 1, let's say here, and if this is the maximum likelihood or the least cost, I will accept this one and I will come to this node. And then again I will see which node will be most beneficial for me, costing me the least. I'll go to that node and I will capture that node, right? So in this way, I can find the entire path. Okay, so you remember Bellman's optimality condition that your dz1 to n can be broken down into dz1 to n minus 1, the optimal part, plus, so basically you already have such something where you have reached, plus this part which is okay, now you are looking at the next nodes, which one I should use to make transition, right? Is this clear? So, okay, just quickly summarizing. So you have this entire rolled out lattice. So lattice is basically this thing where the states are evolving with time, right? This is just a terminology, lattice. So now you have to find the best path. You know the directions. The local constraint is that from this state you can go to either this one or this one or this one. You cannot go back. You cannot go upwards or downwards. You just have to go in the forward direction. And you go step by step and finding the best node to jump to, and then just grab it and move forward, right? This is your greediest approach. I don't know if there can be Anybody can be more greedy than this, but okay. This is a greedy approach. Can we do better than this? We saw in the last class some shortcomings of greedy approach, right? What are the shortcomings? Yes, it will be locally optimal, but globally it might not be optimal. Can I change my search space in such a way that it should be more optimal than this?
At each iterate, change the values of each node and then check that whether for particular node, if the previous three nodes in previous layer, what is giving the minimum. So like
Good. Have you read that before?
that's BP approach. Yeah, we discussed it.
No.
In matrix, finding local minimum.
No, we didn't
So
discuss.
what you do is find the three previous nodes and check what is giving the minimum. So you store all the values. You don't
Okay.
get.
Okay. Did we see this approach in the last class? I don't think so. Maybe. Okay, I don't remember. I don't think so. Okay, so what you do here is, while going from this node to this node, you'd let us say now I have already reached here. I have reached n minus 2 time. Now I want to go. Okay, let us say I have reached n minus 1 time. Right, I have reached here. Now I want to make a transition to tn, right, nth instant. I want to make a transition here, and I want to find which node will be the best. Right? So greedy approach is simply I will make a jump to this one or this one or this one. Just these three values I will compare, which one is the minimum, I will just grab that one and move forward. Right? But a little less greedy approach will be, okay, do not consider that this is the only value you know. Let us say I also know the best paths to reach this one, the best paths to reach this one, as well as the best paths to reach this one. And I have saved now three values, right? I have saved three in my memory. Now I will make a transition from each zn minus 1 to zn minus 2. Let us say, now I will find what is the best path to reach this node, right? It can come from here or here or here. Whichever is the least, I will take that one, and in this way I will reach this node. Now I will find which is the best path to reach this node. Again, I have three possibilities. I will consider all of them, whichever is the minimum. I will use that and I will reach this node. And similarly, I will reach this node. And I will save all these three costs. So basically now I am not tracking a single path. I am tracking three paths. Right? Instead of tracking single paths in DTW, now I am tracking three paths simultaneously. So this is less greedy, right? I have three options. Okay, so this approach, which you just now discovered, is called Viterbi algorithm. So we rename it to your name.
Sir,
In
in the last slide,
the last slide,
in the cost, we also have to maximize the emission probability.
yes,
So each state has a different emission probability for the observations here.
yes,
Don't we also have to consider them during one?
yes, yes. We have to consider. That's why that small d includes both the terms, transition term plus the emission term. So as soon as I go from, let's say, this node to this node, I will add this transition log of transition probability plus the log of emission from this new node. Right? It's possible that the new node is very useless, but there was a high probability of transition to that node. But that it was useless, that will be captured in the emission probability. That will lower down the score. Right? Okay, so this is the Viterbi algorithm, that you have got the path from 0 to n. You do not consider just one path, you are tracking all the k paths. So j can take value from, let us say, 1 to 3 or 1 to whatever number of states are there, k, 1 to capital K. And now, so what is the probability to reach this one is, you consider all the previous nodes, Zn minus 1, over all the i's, make the transition to the new jth node, and in this way, you find the argmax. Right? Clear? So whatever we discussed pictorially, now this is the mathematical representation. So the basic idea is start from n equal to 1 and go sequentially until n equal to capital N. And using this formula, basically tracking k number of paths simultaneously, and then generally what happens, we know the end state Zn. Thus, finally when you reach capital N and you know your end state, then you can eliminate the other two paths and you just take the final path, which is your desired path. An example where we know the final state is, let us say you're doing speech recognition, right? There you exactly know that person will, after when the sentence is over, he will stop speaking, right? It will be a silent state or non-emitting state or something like that, right? You know that the last state will be a silent state. From there you can eliminate all other paths and just take that path. Okay, but if you are not given the final state, if you do not know the final state, what will you do? Yeah, just take the maximum. Simple. Okay. Okay. Is this approach greedy or is this globally optimal? Is this optimal, globally optimal, or is this also somewhat greedy? Optimal? Okay. So, see, what we are considering here, there are how many paths possible? How many paths are possible? How many paths are possible? There are capital K states and capital N time instants. K to the power N. But how many paths we cannot say that actually. How many paths we are able to track? How many paths we are tracking? It's a little complicated calculation. Pardon? Yeah. If you see, finally, we are just tracking k best paths. Finally, we have just tracked from end to end. We have just tracked k best paths. Yeah, best 7. So that's what I'm saying. The best k paths, which are locally optimal in some sense. Locally optimal. It is still possible that, let us say, I have to again give you an example. No problem. Let us say, if you have okay. Okay, let us say the probability here is 0, here it is 1, here it is 0.5, right? Here it is 0.5, here it is 1, here it is 0. I will have to think of an example. No, it is possible that on the way it greedily finds some paths and okay, let me tell you this way. Let us say you have to reach here. You have to choose between these two paths, right? Yeah. Maybe. I think. Yeah, I'm not sure. Let's. Okay. So, but basic idea which I want to convey is this is not a globally optimal solution. This is there is still some possibility that you may mess up your.
Exactly. How are you finding the next path of which for let's say this is a nth layer, it has n plus one layer. So if there's a node there, then how are you getting the optimal path in Python? Exactly. If you are taking all the possible best paths in the previous layer, k layer, and then add that weight of each coming to this node, and then find the minimum from all of them. I think you should get the optimal for that for reaching that node. So there are only k best paths possible for from one layer to the another layer. For one node, there's only one optimal path. So if there are k nodes in one layer, then there are only k optimal paths. So if you are tracking k optimal paths, then there is no need to track any other path.
Yeah, maybe your argument seems good. I will look back into it. Okay, for the time being, let's move on. Okay. Okay, now there is one more situation. Many times we have a sequence evolving through known states. For example, if you say Hari, it will always be the phoneme Ha followed by Shwa or the followed by Ra, followed by E. Right? You cannot have first E, then H, then R, then A. All this that combination is not possible, right? Similarly, in our seasons example, what do you know? In our seasons example, what do you know? You know that spring will come, then summers will come, then autumn will come, then pre-winter, then winter. Like so, this sequence is known. The six seasons. It will never happen that okay that summers have come, then suddenly winter came, then monsoon came, then pre-winter came. That won't happen, right? That sequence is known. But when does each sequence start and when does it end? This exact time alignment is not known, right? Like if I give you data of consecutive 100 days, you know that seasons will appear in that sequence, but you do not know which sequence is on the first day, or sorry, which season is on the first day, which season is on the second day, right? So you have some information but not complete information. Then how do you estimate? So another example here is in music when you let's say a sitar string or any guitar string, if you pluck the string, so the sound has a natural evolution. First there is an onset, there was silence in the beginning, and suddenly the voice raised, there was a tongue, and then the tongue will continue for some time, that is the sustained part, and then release means it will die down after some time eventually. It will die down. So you have three: onset, sustain, release. So how do you model? How can you use HMMs to model this information? The answer is very simple: by constraining your transition probabilities. If you omit certain transitions, these are not possible. Let us say after summers you cannot get winters. So just remove that branch itself. The transition branch only you make zero, like the probability is zero, means the branch is omitted. Then you can get it, right? So that is called left to right HMM, or basically uh, the HMM with transitions which are not allowed, right? So see this example of Hari. When I say Hari, from this state H, her, so this is time in the bottom. This is n and n minus 1 and n, right? So if I say her, so when I'm speaking Hari, it is not, so let us say my time instant is one time window, which is, let us say 10 milliseconds hop and 25 milliseconds window width. That is what generally people use in speech recognition. So I have my one window. Now her sound can continue for several windows, then a sound will continue for several windows, then ra will continue, then e will continue for several windows. How many windows I do not know. That's what I want to estimate. So I'll make a model in this way, that from her you can either stay on her or you can go to a. From a you can either stay on a or go to ra, but you cannot go to her. You cannot go to e. You cannot go to silence. So this is silence. But you can go to ra only or stay on the same state. Similarly with ra, similarly with e. But since e is my last node, e is my last state. So after e, I can go to silence or this dummy state, dummy value of the state, right? And then again, when I want to start my new word, it will start from dummy state. It won't start from or ra or e, but the dummy state will only transition to her. So this on the left, you see the representation of this HMM chain. On the right hand side is the transition diagram, like the trellis, which I can expand as trellis. Is this clear? So in the data which you collected for speech recognition, no, audio event detection, right? Audio event detection data which you collected. Can you use HMMs to model your data, to classify your data? If I give you a recording and ask you, is it door knocking or is it music or speech? Can you use HMMs to do that? Or is it, what other classes were there? Door closing. Right? Door closing has a particular kind of sound, right? Like a burst and then silence. So it starts with a silence, a burst, then again a silence, right? And door knocking will also have some sequence, okay? Burst, 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 or something like that, right? So you can use HMMs to model your temporal data like that. Okay, so some interesting problems that you can solve now. If you know the start and end times of the sequence, but you do not know the start and end times of each state, could you infer that given the trained HMM model? This is what we just now discussed. You know that this start and end time of a sequence means, okay, I'm going to speak Hari, but I do not know what are the exact boundaries of her, ra, and e. Then you can use this Vitabi decoding to exactly find the boundaries for each phoneme. Next is, another interesting problem is inferring season from the temperature of the day. How would you model temperature of the day assuming the seasons as your latent variables? How will you do that? It's very simple, right? You will take 6 latent variables corresponding to your 6 seasons, right? But next is more important. How would you model each season if you know it evolves from start to end? How would you model each season if you know it evolves from start to end? Basically what it means is, now my each season is also evolving. Like summers also start at some time, then attain a peak and then decay. Then the monsoons will start, they will attain a peak and then they will decay. So even within each season also there is variation. How will you do that? Now you know that, okay, the seasons have a sequence. Seasons follow a particular sequence. But even within a season also there is variation. Your temperature is dependent on, this temperature is not following same distribution throughout the season. Even within the season also there is variation in distribution of temperature. How do you model that? Yes, yes. Second layer of latent variables or within each season another latent variable. Okay. Let us say instead of making 6 latent variables, I can make 6 into 3, 18 latent variables. So one latent variable is summer start, summer mid, summer end. Other would be monsoon start, monsoon mid, monsoon end, like that. Right? So you will have 18 latent variables and you do not know the start and end time now. You do not know their start and end times. You may know the start and end time of winter season or summer season, but you do not know what exactly do you call mid-winter, mid-summer, all those things, right? So, but you can use bit-a-bit scheme to find the best fits. It will automatically cluster the data. Okay, this temperature looks like this looks like this looks like this. So there are 3 states: start, mid, and end. Right? Okay. Our approximation, which approximation? x1 will depend on z1. Z1 can take 18 values now, 18 possible values.
So, if we keep a separate gated variable which keeps track of how long has it been since the season change.
Yeah, but then you have to.
Emission transition probabilities will be derived from.
Yes, you can do that, but then your whole mathematics will change, right? Which means your whole code implementation has to be changed, which means another assignment. So you do not do that, right? So that's why people, they try to use standard existing models and work with them rather than changing the whole architecture. Uh, but yes, if it brings some substantial gains, then you can do that. Okay. Now the big question: how do you estimate the parameters of HMM? So always we are considering, given the HMM, how do you infer the states? Given the HMM, how do you find the likelihood of your different latent states? Now, how to estimate the HMM parameters? Should we do that today, or should we? Some people have doubts with NMF or PLCA. Should we discuss that first? Do you have any doubts from what we discussed in the past? NMF or PLCA or anything? No doubts? Okay. Fine, then we'll continue with estimation part. Okay. 3 minutes left. Actually, I think this is a good point to stop because this will be a different topic. This won't take much time, but 3 minutes won't be sufficient. So maybe if you have any questions or doubts, you can ask. So we have our quiz on Sunday evening, right? And the syllabus is before CNNs.
Sir, can you do this joint distribution of
Joint distribution of?
x1, x2, x and z1, z2?
Uh-huh. What is the joint distribution? We derived in the last class, right? We derived this in the last class. So basically you start with Z1, right? Z1 is here. What is the next term? X1 given Z1. X1 given Z1 is also here. Next term will be Z2 given Z1 and X1. And Z2 given X1 won't appear because when Z1 is given. So Z2 given Z1 is here. Then X2 given Z2, Z1, X1. But since you are given Z2, Z1 and X1 won't play a role, so you can give that up, and that term is also here, right? Then you go to the next Z3. Z3 given everything in the past, that will depend only on Z2. So that term is also here, Z3 given Z2. And then X3 given everything, so that will be dependent only on Z3. That term is also here, and you can keep going. Right? Using product rule and the independence properties, you can derive this. Variation within seasons. Yes. So first order Markov models means you're modeling the velocity, right? Because current state given the previous state, it is like velocity. So yes. Yeah, if you have second order Markov model, then it becomes like acceleration. Yeah. Yes. Okay. So we can stop here. Thank you.